At this very moment, a machine the size of a car is drilling into rocks that have not been touched for billions of years on a planet 225 million kilometers away. At this very moment, a spacecraft as large as a school bus is racing toward Jupiter at 51,000 kilometers per hour, headed for a frozen moon hiding a dark ocean beneath its ice. And right now, above your head, astronauts from different nations are floating in separate space stations, running experiments that will decide how far humanity can truly travel beyond Earth. But the most dramatic action isn't happening in space. It's happening in the deserts of Texas. Right now, engineers are assembling the most powerful rocket ever built. A 400-foot tower of steel designed to do something no machine in history has ever done. Fall back from space, be caught in midair by mechanical arms, refueled, and launched again within hours. No recovery ships, no parachutes, no second chances. This is not science fiction. This is not a future prediction. This is not a dream. This is happening now. The new space race is not approaching. It is not being planned. It is not waiting for approval. It has already begun, quietly, relentlessly, and at a scale the world has never seen before. If this journey beyond Earth fascinates you, consider subscribing to Whispering Wonders of Science. Now, let's step into the most ambitious era of space exploration humanity has ever faced. But here's what makes this a space race fundamentally different from the one your grandparents watched on grainy black and white television screens back in the 1960s. Back then, it was two superpowers, two nations, two flags. The United States and the Soviet Union competed in a cosmic game of one-upmanship, each desperate to prove their system superior by planting boots and banners on the moon's dusty surface. It was thrilling. It was historic. It was also finite. Once America won, once Neil Armstrong took that one small step in July of 1969, the urgency evaporated. The funding dried up. The dreams downsized. By 1972, we stopped going. For more than 50 years, no human has ventured beyond low Earth orbit. But something remarkable has happened in the past decade, something that's rewriting the rules of what's possible. This new space race isn't about two countries anymore. It's about dozens of nations and hundreds of companies, all converging on the same cosmic destinations with different technologies, different approaches, and different dreams. This isn't a sprint to plant a flag. This is a marathon to build civilizations. NASA isn't going to the moon just to visit this time. They're going to stay. The European Space Agency isn't sending probes to Mars out of curiosity alone. They're laying groundwork for human habitation. China isn't building a space station for prestige. They're establishing permanent infrastructure in orbit. India isn't launching lunar landers for national pride only. They're proving they can compete with the biggest players in space. And then there are the private companies. Oh, the private companies. SpaceX has launched 138 missions in 2024 alone. 138. That's more than half of all global rocket launches in a single year, accomplished by one company. They're not just launching satellites. They're testing the largest, most powerful rocket ever constructed, designed to carry 100 tons to orbit and land back on Earth to fly again. Blue Origin, funded by Jeff Bezos, just successfully flew their New Glenn rocket, a massive heavy-lift launcher that landed its booster on a drone ship in the Atlantic Ocean. They're planning to send a lunar lander to the moon's south pole in 2026, a private company landing on the moon. Let that sink in. Rocket Lab, a scrappy aerospace company that started in New Zealand, has become the second most prolific launch provider in the world. They're launching satellites every few weeks, and they're building an even bigger rocket. They're even planning to send a probe to Venus in 2026 to search for signs of life in the planet's clouds. This isn't a race between two competitors. This is a stampede, a gold rush, an explosion of capability and ambition unlike anything humanity has ever witnessed. And the destinations. They're not symbolic anymore. They're strategic. They're scientific. They're, dare I say it, economic. The moon isn't just a dead rock we visit for bragging rights. It's a gateway. It has water, frozen in permanently shadowed craters at the poles. Water that can be split into hydrogen and oxygen. Oxygen to breathe. Hydrogen and oxygen to make rocket fuel. Suddenly, the moon isn't just a destination. It's a gas station, a launching pad, a way station for missions deeper into the solar system. Mars isn't just a science project. It's the ultimate test of whether humanity can become a multiplanetary species. Can we grow food in Martian soil? Can we generate oxygen from the thin carbon dioxide atmosphere? Can we protect astronauts from radiation during the 6-month journey? These aren't philosophical questions anymore. NASA, SpaceX, China, and the United Arab Emirates are all actively working on answers. Real hardware, real timelines, real missions. The outer solar system isn't an afterthought. Europa Clipper is en route to Jupiter right now, scheduled to arrive in 2030, where it will study an ice-covered moon that might harbor twice as much liquid water as all of Earth's oceans combined. Dragonfly, a nuclear-powered helicopter drone, will launch to Saturn's moon Titan in 2028, where it will fly through orange skies and land on shores of liquid methane lakes, searching for the chemical precursors to life. Even the asteroids are fair game. China's Tianwen-2 mission will launch in May of 2025 to collect samples from a near-Earth asteroid that might be a fragment of our own moon, blasted into space by some ancient cosmic impact. Japan's space agency is planning missions. The United Arab Emirates is planning missions. Private companies are eyeing asteroids rich in platinum and rare earth elements. Do you see what's happening? Do you feel it? This isn't a race anymore. It's an awakening. It's humanity across all borders, all ideologies, all economic systems, simultaneously deciding that our future lies beyond this blue marble we call home. And the wild part? The most exciting part? We're just getting started. In this video, we're going to explore every major mission currently underway or launching in the next few years. We're going to talk about the moon missions, plural because there are so many. We're going to break down the Mars missions, the outer solar system missions, the revolutionary rockets that make it all possible, and the orbital habitats where humans are learning to live in space permanently. We're going to give you numbers, real dates, specific spacecraft, named missions, because this isn't vague futurism. This is happening. This is scheduled. This is funded. By the end of this video, you won't just understand the new space race. You'll feel the magnitude of this moment. You'll realize that you are living through one of the most consequential eras in human history. The era when we stopped being a single planet species and started becoming something more. So, buckle up. Because the journey we're about to take isn't measured in minutes or hours. It's measured in billions of kilometers, decades of planning, and the dreams of thousands of engineers, scientists, and explorers who refuse to accept Earth's gravity as humanity's final boundary. Let's begin where every great space journey begins, with our closest celestial neighbor. Let's talk about the moon. 384,400 kilometers above your head right now, the moon hangs in space, slowly drifting away from Earth at a rate of about 3.8 centimeters per year. It's been our companion for 4.5 billion years, a silent witness to every moment of human history. And we're about to return, not for a few days, not for a symbolic visit. We're going back to stay. Let's start with the big one, the mission that's capturing global attention, NASA's Artemis program. Artemis, named after Apollo's twin sister in Greek mythology, the goddess of the moon and the hunt, the torchbearer who lights the way. And what a fitting name it is, because Artemis isn't just about revisiting past glories. It's about illuminating a path to the future, Here's the current timeline, and I want you to understand these are real dates, not science fiction. Artemis 1 flew in November of 2022. It was uncrewed, but it was extraordinary. The Space Launch System, the most powerful rocket in operation at that time, launched the Orion spacecraft on a 25-day journey around the Moon. Orion traveled farther from Earth than any spacecraft designed for humans had ever gone before, reaching a maximum distance of 432,000 kilometers from our planet. It tested heat shields, navigation systems, communication networks, and life support systems. It proved the hardware works. Artemis 2 is scheduled to launch no earlier than April of 2026. This will be the first crewed mission beyond low Earth orbit in over 50 years. 4 astronauts, Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen, will ride the Orion capsule around the Moon on a 10-day mission. Victor Glover will become the first person of color to travel to the Moon. Christina Koch will become the first woman to travel to the Moon. Jeremy Hansen will become the first non-American to travel to the Moon. This is history with a capital H, but they won't land. Artemis 2 is a test flight. They'll loop around the Moon, traveling in a trajectory called a hybrid free return, a path that uses the Moon's gravity to slingshot them back toward Earth, even if their engines fail. Safety first. Prove the systems, then push further. Artemis 3, mid-2027. This is the big one. This is when boots touch lunar dust for the first time in over 55 years. But here's where it gets interesting. The lander isn't built by NASA this time. It's built by SpaceX. Remember Starship? That massive stainless steel rocket I mentioned earlier? SpaceX is developing a specialized variant called Starship HLS, Human Landing System. It's enormous. It's taller than a 10-story building. It can carry tons of cargo and crew to the lunar surface and back. But there's a catch. Starship HLS needs fuel. A lot of fuel. More fuel than any rocket can carry from Earth's surface to the Moon in one go. So SpaceX is developing something that sounds like science fiction, orbital refueling. Here's how it works. SpaceX will launch a Starship tanker, a fuel depot, into Earth orbit. Then they'll launch multiple tanker starships, at least 14 of them, each carrying propellant. One by one, they'll dock with the depot and transfer fuel. Once the depot is full, Starship HLS will launch, dock with the depot, fuel up completely, and then boost to the Moon. Has anyone ever done orbital refueling of cryogenic propellants on this scale? Nope. Is it technically challenging? Absolutely. Is SpaceX actually attempting this? Yes. They plan to demonstrate the propellant transfer technology in the spring and summer of 2025. Artemis 3 will send 4 astronauts aboard Orion to lunar orbit, where they'll dock with the pre-positioned Starship HLS. 2 astronauts will transfer to Starship, descend to the lunar surface near the South Pole, spend approximately 6.5 days exploring, collecting samples, and deploying scientific instruments, then return to Orion. The crew will come home as the first humans to visit the Moon in the 21st century. But wait, there's more. So much more. Artemis 4, scheduled for late 2028, will feature the first mission to the Lunar Gateway, a small space station that will orbit the Moon. Think of it as a lunar outpost, a miniature version of the International Space Station, but circling the Moon instead of Earth. Gateway isn't being built by NASA alone. The European Space Agency is contributing modules. The Canadian Space Agency is providing Canadarm3, a next-generation robotic arm. Japan is contributing logistics modules. It's an international effort, and it will serve as a staging point for lunar surface missions, a science laboratory, and a testbed for deep space technologies. Artemis 5, planned for early 2030, will deliver even more Gateway components, including the European Esprit module, Canada's Canadarm3 and NASA's Lunar Terrain Vehicle. Basically, a moon rover that astronauts can drive. Artemis 6 through 11 are already being planned, extending through the mid-2030s. These missions will build out the Artemis base camp on the lunar surface, a permanent habitat where astronauts can live and work for extended periods. We're talking about a foundation habitat, a mobile habitat that can be driven to different locations, power systems, life support systems, and scientific laboratories. This isn't a flags and footprints mission. This is infrastructure. This is permanence. Now, NASA isn't the only one eyeing the moon. SpaceX isn't just building the lander for Artemis. They're using Starship development for their own long-term ambitions, which include lunar missions independent of NASA. Elon Musk has stated that Starship is designed to eventually carry 100 people to the moon or Mars on a single flight. While that's likely decades away, the foundational technology is being tested right now. In 2024, Starship flew 4 test flights. Each one pushed the envelope further. By the 6th flight in November of 2024, both the Super Heavy booster and the Starship upper stage survived re-entry and splashed down in one piece. On the 5th flight in October of 2024, SpaceX achieved something jaw-dropping. They caught the Super Heavy booster out of midair using giant mechanical arms attached to the launch tower, nicknamed the Chopsticks. The rocket, all 23 stories of it, descended from the sky and was plucked out of the air with precision. SpaceX is targeting up to 25 Starship launches in 2025. 25. Each flight tests new systems, new procedures, new capabilities. They're iterating at a pace that makes traditional aerospace look glacial. Now let's talk about Blue Origin's lunar ambitions. Jeff Bezos isn't sitting on the sidelines. Blue Origin's Blue Moon lander program is developing 2 variants: Blue Moon Mark 1, an uncrewed cargo lander, and Blue Moon Mark 2, a crewed lander that can carry astronauts. NASA selected Blue Origin's Blue Moon Mark 2 for the Artemis 5 mission, making Blue Origin an official partner in returning humans to the lunar surface. But Blue Origin isn't waiting for Artemis 5 to prove their technology. They're planning to launch Blue Moon Mark 1 in early 2026 on an uncrewed demonstration mission. The lander will target the region near Shackleton Crater at the moon's south pole, the same area NASA is eyeing for Artemis landings. Blue Moon Mark 1 is an impressive machine. It stands 8 meters tall, masses 21,350 kilograms, and can deliver roughly 3,000 kilograms of payload to the lunar surface. It's powered by Blue Origin's BE-7 engine, which uses liquid hydrogen and liquid oxygen as propellants and can throttle its thrust for precision landing. The demonstration mission will carry NASA's SCALPS instrument, stereo cameras for lunar plume surface studies, which will capture high-resolution images of the rocket exhaust plume as it interacts with the lunar regolith during descent. Why? Because when you land a rocket on the moon, the exhaust kicks up dust and debris. Understanding this plume behavior is critical for safe landings and for protecting nearby equipment. Blue Origin is also developing New Glenn, their heavy-lift orbital rocket, specifically to launch Blue Moon missions. New Glenn flew its first mission in January of 2025, successfully reaching orbit, though the booster didn't stick the landing. The second flight in November of 2025 was a complete success. The booster landed on the drone ship Jacqueline in the Atlantic Ocean, proving the recovery system works. Blue Origin is now planning upgraded versions of New Glenn, including the New Glenn 9x4 variant, which will use 9 BE-4 engines on the first stage and 4 BE-3U engines on the second stage. This monster will be capable of launching over 70,000 kilograms to low Earth orbit and more than 20,000 kilograms on a trans-lunar injection trajectory. It'll be taller than the Saturn V rocket that carried Apollo astronauts to the moon. But governments and billionaire-funded companies aren't the only players in the lunar game. NASA's Commercial Lunar Payload Services Program, CLPS for short, is contracting with multiple private companies to deliver science experiments, technology demonstrations, and equipment to the Moon. In February of 2024, Intuitive Machines became the first private company to successfully land a spacecraft on the Moon. Their Odysseus lander touched down near the lunar South Pole, carrying NASA payloads including instruments to study the lunar environment, test navigation technologies, and analyze the effects of rocket plumes on lunar dust. Odysseus tipped over upon landing and ended up resting on its side, but the mission was still considered a success. The lander operated for several days, transmitting data back to Earth and proving that commercial lunar delivery is viable. Intuitive Machines has more missions planned. IM-2 is scheduled for later in 2025. IM-3 is in the works. Each lander will carry increasingly sophisticated payloads. Astrobotic Technology, another CLPS contractor, flew their Peregrine lander in January of 2024. Unfortunately, a propellant leak shortly after launch doomed the mission, and the lander never made it to the Moon. But Astrobotic learned from the failure, and they're preparing their Griffin lander for a mission later in 2025. Griffin is much larger than Peregrine and is designed to deliver NASA's Viper rover to the Moon. Viper, Volatile's investigating polar exploration rover, is a golf cart-sized robot that will explore the Moon's South Pole, drilling into the regolith to search for water ice. Viper will operate for at least 100 days, mapping the location and concentration of ice deposits. This data is critical for future human missions because water isn't just for drinking. It's rocket fuel. It's radiation shielding. It's the key to sustainable lunar exploration. Firefly Aerospace is another CLPS provider. They're building the Blue Ghost Lander series with the first mission scheduled for 2025. Blue Ghost will carry 10 NASA payloads to the Moon, including instruments to study lunar geology, test communication technologies, and monitor radiation levels. Japan is also heading to the Moon. The Japanese Aerospace Exploration Agency, JAXA, successfully landed their SLIM spacecraft, Smart Lander for Investigating Moon, on the lunar surface in January of 2024. SLIM demonstrated precision landing technology, touching down within 100 meters of its target. That might not sound impressive, but previous lunar landers had accuracies measured in kilometers. SLIM proved you can hit a specific spot on the Moon, which is essential for landing near valuable resources or interesting geological features. Japan isn't stopping there. They're developing a partnership with India called LUPEX, Lunar Polar Exploration Mission, which will send a rover to the Moon's South Pole to search for water ice. They're collaborating with the United States on crewed lunar missions, and they're working on the Martian Moon's Exploration Mission, MMX, which, while focused on Mars, uses similar technologies being developed for lunar exploration. Speaking of India, their space program is on fire right now. In August of 2023, India became the fourth country to successfully soft land a spacecraft on the Moon when their Chandrayaan-3 mission touched down near the lunar South Pole. The lander and rover operated for 1 lunar day, about 14 Earth days, conducting experiments and capturing stunning images of the lunar surface. India's follow-up missions are ambitious. Chandrayaan-4 is being planned as a sample return mission, which would make India only the fourth country to bring lunar samples back to Earth. They're also working on international partnerships, collaborating with Japan on LUPEX and with NASA on various lunar science projects. And then there's China. Oh boy, China. China's lunar program is moving at an astonishing pace. Let's recap what they've already accomplished. Chang'e 4 landed on the far side of the Moon in January of 2019. The far side, the hemisphere we never see from Earth, because the Moon is tidally locked. No one had ever landed there before because there's no direct radio communication with Earth from the far side. China solved this by launching the Queqiao relay satellite to a special orbit where it can see both the far side of the Moon and Earth simultaneously. Chang'e 4 is still operating, collecting data on the far side's geology and testing technologies. Chang'e 5 flew in November of 2020 and returned samples from the near side of the Moon, the first lunar samples brought back to Earth since the Soviet Union's Luna 24 mission in 1976. Scientists are still analyzing these samples, and they've already revealed new insights into lunar volcanism. Chang'e 6 launched in May of 2024 and achieved something extraordinary. It collected samples from the far side of the Moon and returned them to Earth in June. This was a first in human history. No one had ever retrieved material from the far side before. The samples landed in Inner Mongolia, and Chinese scientists are now studying material that might hold clues to the Moon's early history. After delivering the samples, the Chang'e 6 orbiter didn't go into retirement. It was commanded to travel to the Sun-Earth L2 Lagrange point, a gravitationally stable location in space where it can observe both the Sun and Earth. China is using it for extended mission testing, but China's lunar ambitions go way beyond robotic missions. They've announced plans to land Chinese astronauts, taikonauts, on the Moon by 2030. And they're not just talking, they're building the hardware. The Long March 10 rocket is under development specifically for crewed lunar missions. It's a heavy-lift launcher comparable to NASA's Space Launch System. The Mengzhou spacecraft is China's next-generation crewed vehicle, designed to carry taikonauts to the Moon. It features a modular design with a return capsule and a service module, and it's larger than the Shenzhou spacecraft currently used for trips to China's Tiangong space station. The Lanyo lunar lander is being developed to carry 2 taikonauts to the Moon's surface. China plans to demonstrate Mengzhou in an uncrewed orbital test flight in late 2026, launching it aboard a Long March 10A rocket and docking it with the Tiangong space station. This will validate the spacecraft's systems before committing to lunar missions. China is also working on Chang'e 7 and Chang'e 8 missions, planned for the late 2020s. These will explore the lunar South Pole with landers, rovers, and possibly even a small flying probe. Chang'e 8 will test in-situ resource utilization technologies, essentially using lunar materials to build structures or extract useful resources. The long-term goal? China wants to establish an International Lunar Research Station, ILRS, in partnership with Russia and potentially other nations. It would be a permanent lunar base, similar in concept to NASA's Artemis Base Camp, but developed independently. The European Space Agency isn't planning crewed lunar missions on their own, but they're deeply involved in Artemis. ESA is building the service modules for NASA's Orion spacecraft, the part that provides propulsion, power, water, and air for the crew. Without ESA's contributions, Artemis couldn't fly. ESA is also developing the Argonaut lunar lander, a cargo vehicle that could deliver up to 1.5 tons of payload to the Moon's surface. They've selected 3 companies, Thales Alenia Space, OHB, and Ariane Group, to conduct design studies with the goal of flying Argonaut missions in the late 2020s. Russia has announced lunar ambitions, but their program has faced setbacks. The Luna 25 mission, which was supposed to land near the Moon's South Pole in August of 2023, crashed due to a propulsion system failure. It was Russia's first moon mission since Luna 24 in 1976, and the failure was a significant blow. Luna 26 and Luna 27 missions are still planned, but timelines have become uncertain. The United Arab Emirates is also getting into the lunar game. They've announced plans for the Rashid 2 rover, a follow-up to the Rashid rover that was lost when the Japanese Hakuto R lander crashed in 2023. The UAE is also working on a lunar orbiter mission and has expressed interest in participating in the International Lunar Research Station with China and Russia. Even South Korea is heading to the Moon. Their Danuri orbiter, also called the Korean Pathfinder lunar orbiter, has been circling the Moon since August of 2022. mapping the surface and testing communication technologies. South Korea is planning follow-up missions, including a possible lunar lander. Do you see the pattern here? It's not just NASA. It's not just SpaceX. It's not just China. It's everyone. Dozens of nations and companies, all converging on the moon simultaneously. Why? Because the moon has water. Let me explain why this is such a big deal. For decades, scientists thought the moon was bone dry. The Apollo astronauts brought back samples that seemed devoid of water. We assumed the moon's formation, likely the result of a massive collision between early Earth and a Mars-sized object, had vaporized any water that might have existed. But we were wrong. In 2009, NASA's L-Cross mission slammed a rocket stage into a permanently shadowed crater at the moon's south pole and analyzed the debris plume. The results were stunning. Water ice. Lots of it. Subsequent missions confirmed it. India's Chandrayaan-1 found evidence of water molecules across the lunar surface. NASA's Lunar Reconnaissance Orbiter detected signatures of ice in shadowed craters. China's Chang'e missions found water in lunar soil samples. The permanently shadowed regions at the moon's poles are some of the coldest places in the solar system, colder than the surface of Pluto. Sunlight hasn't touched these areas in billions of years. Water ice can accumulate there, delivered by comets and asteroids over eons, and it just stays. Estimates suggest there could be hundreds of millions of tons of water ice at the lunar poles. Now, why does this matter? Water is heavy. Launching water from Earth to the moon costs thousands of dollars per kilogram. But if there's already water on the moon, you don't need to bring it from Earth. You can drink it, obviously, but you can also electrolyze it, split it into hydrogen and oxygen using electricity from solar panels. Oxygen to breathe. Hydrogen and oxygen are also the most efficient rocket propellants we know. Combine them in a rocket engine, and you get tremendous thrust and high efficiency. This means the moon can become a refueling station. Launch a spacecraft from Earth with minimal fuel, stop at the moon to fill up, then continue to Mars or the asteroids or beyond. You've just made deep space exploration exponentially cheaper and more feasible. Water ice can also be used for radiation shielding. Space is filled with high-energy particles, cosmic rays, solar radiation that can harm astronauts. A few meters of water surrounding a habitat provides excellent shielding. Suddenly, the moon isn't just a scientific curiosity, it's strategic infrastructure. It's the difference between visiting space and living in space. That's why everyone is racing there. That's why NASA is building Artemis Base Camp at the South Pole. That's why China is targeting the same region. That's why commercial companies are developing lunar landers. The nation or entity that figures out how to extract and utilize lunar water first will have a massive advantage in the next phase of space exploration. And it's happening now. Artemis 2 launches in April of 2026. Artemis 3 lands astronauts in mid-2027. Blue Moon Mark 1 flies in early 2026. China aims for 2030. Commercial landers are touching down throughout 2025 and beyond. This is real. This is scheduled. This is happening. But the moon, as exciting as it is just the beginning. Because while dozens of missions are converging on our closest neighbor, humanity's gaze is fixed on a more distant prize, a rusty, cold, windswept world that captures our imagination like no other. Mars. Right now on the surface of Mars, a robot named Perseverance is alone. Well, not entirely alone. There are other robots there, orbiters circling overhead, the dormant remains of previous rovers. But Perseverance is the only active surface mission. And what it's doing right now might be the most important scientific work happening anywhere in the solar system. Perseverance is collecting samples. Let me paint the picture of just how incredible this is. Mars is approximately 225 million kilometers from Earth right now. The distance varies because both planets orbit the Sun at different speeds, but on average you're looking at about 7 light minutes of distance. That means when engineers at NASA's Jet Propulsion Laboratory in California send a command to Perseverance, it takes 7 minutes for that signal to reach Mars, then another 7 minutes for a response to come back, 14-minute lag for every communication. Perseverance cannot be controlled like a video game. It has to think for itself, and it's doing extraordinary work. The rover landed in Jezero Crater in February of 2021. Jezero is a dried-up ancient lakebed, a place where water once pooled billions of years ago. If life ever existed on Mars, and that's still a very big if, Jezero Crater is one of the best places to look. Perseverance is equipped with a robotic arm tipped with a drill. It approaches rocks, drills into them, extracts cylindrical core samples about the size of a piece of chalk, seals them in ultra-clean titanium tubes, and deposits them on the Martian surface. As of now, Perseverance has collected dozens of samples. Each one represents a different type of rock, a different geological story, a potential window into Mars's ancient past. These samples are sitting on Mars right now, waiting for the Mars Sample Return mission. If you want to understand just how ambitious humanity has become in space exploration, Mars Sample Return is the perfect example. It's the most complex robotic mission ever attempted. Here's how it's supposed to work. First, NASA and the European Space Agency will launch the Sample Retrieval Lander sometime in the early 2030s. This lander will carry 2 things: a small fetch rover and the Mars Ascent Vehicle, MAV. The fetch rover will drive around Jezero Crater, locate the sample tubes Perseverance has cached, and bring them back to the lander. Perseverance might also drive some samples directly to the lander if it's still operational. Once the samples are collected, they'll be loaded into the Mars Ascent Vehicle. The MAV will then become the first rocket ever launched from the surface of another planet. It'll blast off from Mars and climb into orbit, carrying the precious samples in a container about the size of a basketball. Meanwhile, an Earth Return Orbiter, ERO, will already be circling Mars. This spacecraft, built by ESA, will locate the basketball-sized sample container in Martian orbit, approach it, capture it using a robotic arm, and seal it inside a biocontainment system. We don't know if there's life in those samples, but we're not taking chances. The ERO will then fire its engines and begin the long journey back to Earth. When it arrives, it won't land. Instead, it'll release the sample container, which will plunge through Earth's atmosphere and parachute down to a landing site in the Utah desert, where it'll be recovered and transported to a specially designed containment facility. If this all works, if every single piece of this interplanetary relay race functions perfectly, we'll have rocks from Mars in laboratories on Earth sometime in the middle 2030s. Scientists will be able to study these samples with instruments that are far too large and complex to send to Mars. They'll be able to search for biosignatures, chemical or structural evidence of past microbial life. They'll be able to date the rocks precisely, understanding Mars's geological timeline. They'll be able to analyze mineral compositions that tell the story of ancient water, ancient climates, ancient possibilities. But there's a problem. As of late 2024 and into 2025, Mars Sample Return is in trouble. The mission's projected cost has ballooned to over $11 billion. NASA's budget is tight. Political support is uncertain. There have been discussions of scaling back the mission, delaying it, or even canceling it. Scientists are fighting to keep it alive because the scientific payoff is incalculable. But the political and financial realities are harsh. So Perseverance's samples sit on Mars, waiting, hoping. But let's talk about what else is happening at Mars, because there's plenty. Perseverance had a companion, Ingenuity. Ingenuity was a tiny helicopter weighing just 1.8 kilograms, designed to test whether powered flight is even possible in Mars's incredibly thin atmosphere. Mars's atmospheric pressure is less than 1% of Earth's. Flying there is like flying at 100,000 feet altitude on Earth, higher than any helicopter has ever gone. NASA planned for Ingenuity to make 5 flights over 30 days. Just a technology demonstration. Prove the concept and move on. Ingenuity flew 72 times over nearly 3 years. 72 flights. It scouted routes for Perseverance, explored areas too dangerous for the rover, captured stunning aerial images of the Martian landscape, and demonstrated that rotorcraft can be invaluable tools for Mars exploration. Sadly, Ingenuity's mission ended in January of 2024 when damage to its rotor blades during landing left it unable to fly. But what a legacy. It proved that we can fly on Mars. Future missions will include helicopters, drones, maybe even fixed-wing aircraft. Meanwhile, NASA's Curiosity rover is still chugging along. It landed in Gale Crater way back in August of 2012, and it's still operational 13 years later. Curiosity is slowly climbing Mount Sharp, a 5-kilometer tall mountain in the center of Gale Crater, studying different geological layers that represent different eras in Mars's history. Curiosity has made incredible discoveries, evidence of ancient riverbeds, organic molecules in Martian rocks, methane spikes in the atmosphere that hint at possible subsurface activity. It's a rolling laboratory, and it's still delivering groundbreaking science. There are also multiple orbiters circling Mars, acting as communication relays and science platforms. NASA's Mars Reconnaissance Orbiter has been operational since 2006, capturing high-resolution images of the Martian surface and monitoring weather patterns. NASA's MAVEN orbiter studies Mars's upper atmosphere, helping us understand how the planet lost most of its atmosphere over billions of years. ESA's Trace Gas Orbiter, part of the ExoMars program, is searching for trace gases in the Martian atmosphere, including methane, which could indicate biological or geological activity. India's Mars orbiter mission, Mangalyaan, operated from 2013 until communication was lost in 2022, making India the first Asian nation to reach Mars. The United Arab Emirates Hope orbiter arrived at Mars in February of 2021. It's studying Mars's atmosphere and weather patterns, providing a global view of how the atmosphere behaves across different times of day and different seasons. China's Tianwen-1 mission is particularly impressive. It launched in July of 2020, and it consisted of an orbiter, a lander, and a rover. In May of 2021, the lander successfully touched down in Utopia Planitia, and the Zhurong rover began exploring the surface. Zhurong operated for about a year before entering hibernation during the Martian winter. As of 2025, efforts to wake it up have been unsuccessful, but the mission was still considered a success. China proved they could land on Mars, operate a rover, and conduct scientific research. That's a huge technological achievement. The next big Mars mission launching soon is NASA's ESCAPADE, Escape and Plasma Acceleration and Dynamics. Explores. This mission consists of 2 small satellites that will study Mars's magnetosphere and how the solar wind strips away the Martian atmosphere. ESCAPADE launched in November of 2025 aboard Blue Origin's New Glenn rocket. It'll arrive at Mars in late 2026. But what everyone really wants to know is, when are humans going to Mars? The honest answer is, it's complicated. NASA has stated goals of sending humans to Mars in the 2030s. SpaceX CEO Elon Musk has suggested much more aggressive timelines, talking about uncrewed Starship missions to Mars as early as 2026 and crewed missions potentially in the early 2030s. Let's break down the challenges because they are immense. First, there's the distance. Mars is far. Really far. Depending on where Earth and Mars are in their orbits, the distance varies from about 54 million kilometers at closest approach to over 400 million kilometers when they're on opposite sides of the Sun. The most fuel-efficient trajectory to Mars is called a Hohmann transfer orbit. You launch when Earth and Mars are properly aligned, coast for about 6 to 9 months, and arrive when Mars is in the right position. This alignment happens roughly every 26 months, which means you have a limited launch window, 6 to 9 months in a cramped spacecraft. No turning back, no emergency abort to Earth. Then there's radiation. In low Earth orbit, astronauts aboard the International Space Station are partially protected by Earth's magnetic field. On the way to Mars, there's no such protection. Cosmic rays and solar particle events can deliver dangerous radiation doses. Shielding helps, but it adds mass which makes the spacecraft heavier, which requires more fuel. Some proposed solutions include using water or food storage as radiation shielding, or creating a storm shelter, a heavily shielded compartment where astronauts can take refuge during solar events. Life support is another massive challenge. The ISS has resupply missions from Earth every few months. Mars astronauts won't have that luxury. They'll need closed-loop life support systems that recycle water, generate oxygen, and handle waste for the entire multi-year mission. Psychological factors matter too. Mars astronauts will experience isolation unlike anything in human history. Earth will be a tiny dot in the sky. Communication delays will make real-time conversations impossible. The crew will need to function as a self-sufficient team for years, dealing with stress, boredom, interpersonal conflicts, and the knowledge that help is millions of kilometers away. Landing on Mars is tricky. Mars has enough atmosphere to require a heat shield during entry, but not enough atmosphere for parachutes to slow you down sufficiently. Every Mars lander has used a combination of heat shields, parachutes, and retro rockets. Scaling this up to land something large enough to carry humans and their equipment is a major engineering challenge. Then there's the surface mission. What will astronauts do on Mars? They'll need habitats, power systems, rovers, scientific equipment. They'll need to extract resources from the Martian environment, water from ice deposits, oxygen from the carbon dioxide atmosphere. They'll need spare parts, tools, medical supplies, and eventually, they'll need to come home. That means launching from Mars, which requires fuel. Lots of fuel. SpaceX's plan involves producing methane fuel on Mars, using the Sabatier reaction, combining carbon dioxide from the atmosphere with hydrogen brought from Earth or extracted from Martian ice. NASA's approach is more methodical. They're planning a series of precursor missions to test technologies before committing to human flights. This includes Mars Sample Return, which demonstrates key technologies like launch from Mars and rendezvous in Martian orbit. SpaceX's approach is more aggressive. They're developing Starship with Mars in mind from the start. The spacecraft is designed to carry 100 tons of payload to Mars's surface. Elon Musk has talked about sending multiple cargo starships to Mars during the 2026 launch window. Uncrewed missions carrying supplies, equipment, and fuel production plants. If those missions succeed, crewed missions could follow in 2028 or 2030. Is that realistic? Maybe. SpaceX has a track record of achieving things people said were impossible. They've landed orbital rockets. They've built the largest rocket ever flown. They've reduced launch costs by an order of magnitude. But sending humans to Mars is orders of magnitude harder than anything SpaceX has done before. There's no margin for error, no rescue mission. You have to get everything right. China has also announced long-term Mars ambitions. They're planning robotic sample return missions in the late 2020s and have stated goals of landing taikonauts on Mars in the 2040s or later. The European Space Agency and Russia were partners on the ExoMars program, which included a planned rover mission, but collaboration has been complicated by geopolitical tensions. ESA is now exploring independent Mars missions or potential partnerships with NASA. So when will humans walk on Mars? Honestly, probably in the 2030s or early 2040s. It's going to happen. The technology is advancing. The political will is building. The private sector is investing, but it's not going to be easy. It's going to require international cooperation, massive investment, brilliant engineering, and a healthy dose of courage from the astronauts who make the journey. Mars is the next giant leap for humanity. Not because it's easy, but because it's hard, because it challenges us to become better, smarter, more resilient, because it forces us to answer the question, can we become a multiplanetary species? The answer, I believe, is yes. But while Mars dominates the conversation about human exploration, it's not the only destination capturing our attention. Because beyond Mars, deeper in the solar system, there are worlds so strange, so alien, so potentially life-bearing, that they demand our exploration. Let's journey to the outer realms. None of this, absolutely none of it, would be possible without the ability to launch payloads into space reliably, frequently, and affordably. And we are living through a revolution in launch capabilities that is reshaping everything. Let's start with the elephant in the room, SpaceX. In 2024, SpaceX launched 138 missions. 138 times a Falcon 9 or Falcon Heavy rocket roared off the pad, delivered payload to orbit, and most of the time landed back on Earth to fly again. To put that in perspective, 138 launches is more than half of all orbital launches conducted globally in 2024. One company, more than half the world's launches. It's absurd, it's unprecedented, and it's accelerating. SpaceX's workhorse is the Falcon 9, a two-stage rocket that can lift approximately 22.8 metric tons to low Earth orbit. The first stage is reusable. After separating from the upper stage, it relights its engines, performs a controlled descent, and lands either on a drone ship in the ocean or at a ground landing site. As of late 2024, SpaceX has successfully landed the Falcon 9 first stage over 200 times. 200? Some individual boosters have flown more than 20 times. Booster 1082, for example, has flown 18 times. That's 18 missions on the same piece of hardware. This is a complete paradigm shift. Traditional rockets were expendable. You spent hundreds of millions of dollars building a rocket, used it once, and threw it away. SpaceX proved you could land it, refurbish it, and fly it again, and again, and again. The economics are staggering. A Falcon 9 launch costs approximately $67 million, but the majority of that cost is the upper stage, payload integration, fuel, and operations. The first stage, which represents a huge chunk of the rocket's value, is reused. If SpaceX were building a new first stage for every mission, costs would be multiples higher. Reusability is why SpaceX can launch so frequently. They're not bottlenecked by rocket production. They're bottlenecked by payload availability, launch pad schedules, and regulatory approvals. And then there's Starship. We've talked about Starship in the context of lunar and Mars missions, but let me emphasize just how revolutionary this vehicle is. Starship is the largest, most powerful rocket ever built. The full stack, Super Heavy booster, plus Starship upper stage, stands 122 meters tall. That's taller than the Statue of Liberty. It's taller than a 40-story building. The Super Heavy booster is powered by 33 Raptor engines burning liquid methane and liquid oxygen. At liftoff, it produces approximately 7,400 tons of thrust. For comparison, the Saturn V that took astronauts to the moon produced about 3,400 tons of thrust. Starship produces more than twice that. The Starship upper stage itself has 6 Raptor engines, 3 optimized for sea-level operation and 3 optimized for vacuum. It's designed to carry payloads of 100 to 150 metric tons to low Earth orbit in its reusable configuration, or potentially more in expendable mode. And the entire system is designed to be fully reusable. Both stages land back on Earth. Both can be refueled and flown again. SpaceX's goal is same-day turnaround. Launch in the morning, land, refuel, launch again in the afternoon. No one has ever done that. It's never been attempted. It sounds like science fiction. But SpaceX is demonstrating it piece by piece. In October of 2024, on Starship's 5th test flight, they caught the Super Heavy booster out of midair using the launch tower's mechanical arms. The booster descended from the sky, aligned itself with the tower, and was grabbed at precise hardpoints. It was one of the most jaw-dropping moments in spaceflight history. SpaceX is targeting up to 25 Starship test flights in 2025. They've received provisional approval from the FAA to increase annual launches from their Texas Starbase site from 5 to 25, and they're building additional launch infrastructure at Kennedy Space Center in Florida. Each test flight is pushing boundaries. Flight 7, planned for early 2025, will attempt the first payload deployment, 10 Starlink satellite simulators. Flight 8 might attempt catching the Starship upper stage with the tower. Future flights will test in-orbit refueling, long-duration coast phases, and re-entry from orbital velocities. If SpaceX achieves full Starship reusability, the cost per kilogram to orbit could drop by 1 or 2 orders of magnitude. We're talking about launch costs that make space infrastructure, solar power satellites, large space stations, fuel depots, economically viable for the first time. But SpaceX isn't the only company innovating. Blue Origin's New Glenn rocket just became operational. After years of development delays, New Glenn flew its maiden flight in January of 2025, successfully placing a payload into orbit. The second flight in November of 2025 was a complete success. The booster landed on the drone ship Jacqueline, proving the recovery system works. New Glenn is a heavy lift, partially reusable rocket. The first stage uses 7 BE-4 engines, burning liquid oxygen and liquid methane. It can deliver 45 metric tons to low Earth orbit in its baseline 7x2 configuration. But Blue Origin isn't stopping there. They've announced the New Glenn 9x4 variant, which will use 9 BE-4 engines on the first stage and 4 BE-3U engines on the second stage. This upgraded version will lift over 70 metric tons to low Earth orbit and will be taller than the Saturn V. Blue Origin's vision is to operate both the 7x2 and 9x4 variants concurrently, giving customers options based on payload mass and mission requirements. The 7x2 is perfect for most commercial satellite launches and even some lunar missions. The 9x4 can handle the heaviest payloads, including components for Blue Origin's Orbital Reef Commercial Space Station. Jeff Bezos has stated that Blue Origin's long-term goal is to move heavy industry off Earth and into space. New Glenn is a critical part of that vision. The rocket's payload fairing is 7 meters in diameter, large enough to carry massive structures or pre-assembled satellite components. Blue Origin is also upgrading the BE-4 engines to produce more thrust. The current engines generate approximately 550,000 pounds of thrust each. The upgraded versions will produce 640,000 pounds of thrust each. That's a 15% increase, which translates to significantly higher payload capacity. Now, let's talk about Rocket Lab, the scrappy underdog that's become the second most prolific launch provider in the world. Rocket Lab's Electron rocket is a small 2-stage launcher designed to carry up to 300 kilograms to low Earth orbit. It's tiny compared to Falcon 9 or New Glenn, but that's the point. Electron is optimized for small satellite missions, constellations, Earth observation satellites, technology demonstrations, science missions. In 2024, Rocket Lab launched 12 Electron missions, breaking their previous record. In 2025, they're on track to launch even more. They have contracts lined up for years, multiple missions for the Japanese company, IQPS, constellation deployment for Synspective, NASA science missions, military payloads, and commercial customers. Electron uses a unique engine design. The Rutherford engines are powered by electric pumps, driven by batteries, rather than traditional turbopumps, driven by gas generators or preburners. This makes the engines simpler, lighter, and easier to manufacture. Rocket Lab 3D prints the Rutherford engines using electron beam melting, a sophisticated additive manufacturing process. Rocket Lab has also started recovering and reusing Electron first stages. They use a helicopter to catch the descending stage mid-air under parachute, then refurbish it for another flight. It's a different approach than SpaceX's propulsive landing, but it works. But Rocket Lab's most exciting project is Neutron, a medium-lift rocket designed to compete with Falcon 9. Neutron is scheduled for its first launch in late 2025 or early 2026. Neutron will be capable of lifting 13 metric tons to low Earth orbit in its reusable configuration. Like Falcon 9, the first stage will land back on Earth, but Rocket Lab is designing Neutron to land on an offshore platform called Return on Investment. What makes Neutron unique is its payload fairing design. Instead of a traditional fairing that splits in half and falls away, Neutron has a hungry hippo fairing that opens like a giant mouth and spits out the upper stage. It sounds bizarre, but it allows the fairing to remain attached to the first stage, reducing the number of parts that need to be recovered. Rocket Lab has secured major contracts for Neutron even before it flies. They have deals for national security launches, commercial satellite deployments, and even a potential contract to deliver cargo to the Moon as part of NASA's CLPS program. Rocket Lab is also planning one of the most audacious missions I've ever heard of, the Venus Life Finder. They're developing a small probe designed to plunge through Venus's atmosphere, collecting samples of the clouds at altitudes between 47 and 60 kilometers, where temperatures and pressures are relatively benign. The probe will search for organic molecules, potential signs of microbial life floating in Venus's acidic clouds. This mission is scheduled to launch aboard an Electron rocket in summer of 2026. A private company searching for life on another planet? That's the world we're living in now. Beyond these major players, there's a whole ecosystem of new launch providers. Relativity Space is developing the Terran R rocket, a medium-lift launcher that's almost entirely 3D printed. They're targeting reusability and rapid manufacturing. Firefly Aerospace is developing the Alpha rocket for small satellite launches and the MLV medium launch vehicle for heavier payloads. ABL Space Systems is working on their RS-1 rocket for responsive launch operations. In Europe, Arianespace successfully launched the new Ariane 6 rocket in July of 2024, replacing the retired Ariane 5. Ariane 6 is a modular design that can be configured with 2 or 4 solid rocket boosters, depending on payload requirements. It's not reusable yet, but Arianespace is studying options for future upgrades. Arianespace also flew the upgraded Vega C rocket in December of 2024. Vega C is designed for smaller payloads and offers Europe an independent option for launching scientific missions and Earth observation satellites. In China, the state-owned launch providers are ramping up cadence. The Long March rocket family flew dozens of missions in 2024, supporting China's space station program, lunar missions, commercial satellite constellations, and military payloads. But China is also seeing the rise of private space companies. Galactic Energy, iSpace, Landspace, and others are developing commercial launch vehicles. Some of these companies are pursuing reusability, copying SpaceX's approach. Japan's space agency, JAXA, is developing the H-3 rocket to replace the aging H-2A. H-3 is designed to be more cost-effective and versatile, capable of carrying payloads to geostationary transfer orbit, lunar trajectories, and beyond. India's ISRO is upgrading their GSLV and PSLV rockets and developing new variants to support increased launch demand. India is also working on reusable launch vehicle technologies, conducting test flights of a winged spaceplane demonstrator. Russia continues to launch Soyuz and Proton rockets, but their launch cadence has decreased in recent years due to economic pressures and geopolitical sanctions. The future of Russia's space program is uncertain. The overall trend is clear. Launch is becoming routine, frequent, and affordable. We're moving from an era where every launch was a national event to an era where multiple launches happen every single day somewhere in the world. This is the foundation. This is what makes everything else possible. You can't build a lunar base without reliable, frequent launches. You can't send humans to Mars without heavy-lift rockets. You can't deploy satellite constellations without low-cost access to orbit. The launcher revolution is enabling the space revolution. And as launch becomes cheaper and more accessible, the destinations we can reach expand dramatically. We've talked about the Moon and Mars, but there are worlds beyond the red planet that are calling to us. Worlds of ice and fire, of alien oceans and methane rains, of mysteries we're only beginning to unravel. It's time to journey to the outer realms. Let me tell you about a place so alien, so utterly unlike Earth, that it challenges everything we think we know about where life can exist. It's a moon. Not our moon, but one of Jupiter's. It's called Europa. Europa is slightly smaller than Earth's moon, but beneath its icy crust lies a secret. A global ocean of liquid water, possibly 100 kilometers deep, containing more water than all of Earth's oceans combined. And right now, a spacecraft is on its way there. Europa Clipper launched in October of 2024 aboard a SpaceX Falcon Heavy rocket. It's the largest planetary science spacecraft NASA has ever built. When its solar panels are deployed, they span 30 meters, longer than a basketball court. Europa Clipper isn't going straight to Jupiter. That would require too much fuel. Instead, it's using gravity assists. In February of 2025, it'll swing past Mars, using the red planet's gravity to change its trajectory and gain speed. In December of 2026, it'll fly past Earth, getting another gravitational boost. Then it's off to Jupiter, arriving in April of 2030. Why all this effort for a moon? Because Europa might harbor life. Let me explain. Europa's surface is a shell of water ice, crisscrossed with cracks and ridges. Beneath that ice, scientists believe there's a global ocean kept liquid by tidal heating. Jupiter's immense gravity pulls on Europa, and the gravitational tug of Europa's neighboring moons creates tidal forces that flex the moon's interior, generating heat through friction. This ocean has been liquid for potentially billions of years. It's in contact with a rocky seafloor, which means minerals and chemicals could dissolve into the water, providing nutrients. There might even be hydrothermal vents on Europa's ocean floor, similar to the ones on Earth, where entire ecosystems thrive without sunlight. Europa Clipper won't land on the moon. Instead, it'll orbit Jupiter and make nearly 50 close flybys of Europa, dipping as low as 25 kilometers above the surface. It carries 9 scientific instruments, ice-penetrating radar to probe beneath the surface and map the ice shell's thickness, magnetometers to study Europa's magnetic field, which can tell us about the ocean's salinity and conductivity, cameras to capture high-resolution images of the surface, looking for evidence of recent geological activity, spectrometers to analyze the composition of surface materials and any plumes of water vapor that might be erupting from cracks in the ice. Yes, plumes. The Hubble Space Telescope has observed what appear to be water vapor plumes erupting from Europa's surface, possibly reaching heights of 200 kilometers. If Europa Clipper flies through one of these plumes, it could sample fresh ocean water without even landing. Imagine that, sampling an alien ocean. From orbit, Europa Clipper will spend about 4 years at Jupiter, conducting its flybys, collecting data, and sending it back to Earth. If it finds compelling evidence of habitability, or dare I say, biosignatures, it would revolutionize our understanding of life in the universe. But Europa isn't the only icy moon with an ocean. Saturn's moon, Enceladus, is smaller than Europa, but it's no less intriguing. Enceladus has geysers, massive plumes of water vapor, and ice particles erupting from cracks near its south pole, shooting hundreds of kilometers into space. NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew through these plumes multiple times. It analyzed their composition and found water, salt, organic molecules, and even molecular hydrogen, a potential energy source for microbial life. Enceladus's plumes are direct samples of its subsurface ocean. We don't need to drill through ice. We just need to fly through the plume and collect particles. There's no dedicated mission to Enceladus yet, but scientists are planning. Proposals include an Enceladus orbiter that would make multiple plume passes, or even a lander that could sit near the South Pole and collect freshly fallen plume material. And then there's Titan. Titan is Saturn's largest moon and the only moon in the solar system with a thick atmosphere. When I say thick, I mean thick. Titan's atmospheric pressure at the surface is 1.5 times Earth's. If you stood on Titan, you'd experience roughly the same air pressure as you do at sea level on Earth. But Titan's atmosphere is nothing like ours. It's mostly nitrogen, with traces of methane and other hydrocarbons. Temperatures at the surface are minus 179 degrees Celsius. It's so cold that water ice is as hard as rock, and liquid methane takes the role of water. Titan has lakes, rivers, seas, all made of liquid methane and ethane. Radar images from Cassini show lakes at Titan's poles, some larger than North America's Great Lakes. There are river channels carved by flowing methane. There's a hydrological cycle. Methane evaporates, forms clouds, rains down, and flows into lakes. It's Earth-like, but utterly alien. And NASA is sending a mission there. Dragonfly is a dual quadcopter lander, a robotic drone powered by a nuclear battery. It's scheduled to launch in July of 2028 aboard a SpaceX Falcon Heavy and will arrive at Titan in the mid-2030s. Dragonfly will explore Titan by flying. It'll take off, fly several kilometers, land at a new location, conduct science, then fly again. Over the course of its mission, it'll visit dozens of locations, covering hundreds of kilometers. Why Titan? Because it's a natural laboratory for prebiotic chemistry. Titan has all the ingredients you'd need for life: carbon-based molecules, nitrogen, water ice, and energy from sunlight and cosmic rays. It's like a frozen version of early Earth, before life emerged. Dragonfly will analyze Titan's surface composition, search for complex organic molecules, study the atmosphere, and even drill into the surface to collect samples. If it finds evidence of chemistry that's trending toward life, molecules organizing themselves into more complex structures, it would be groundbreaking. Closer to the Sun, there's Mercury, the smallest planet, the closest planet to the Sun, a scorched, airless rock pummeled by solar radiation. And yet, we're still learning its secrets. Bepi Colombo is a joint mission by the European Space Agency and Japan's JAXA. It launched in October of 2018 and has been making a series of gravity-assist flybys of Earth, Venus, and Mercury to slow down enough to enter Mercury's orbit. Bepi Colombo made its sixth flyby of Mercury in January of 2025. It will enter orbit around Mercury in November of 2026, where it will split into two separate spacecraft. The Mercury Planetary Orbiter, built by ESA, will study Mercury's surface and interior. The Mercury Magnetospheric Orbiter, built by JAXA, will study Mercury's magnetic field and its interaction with the solar wind. Mercury is weird. It's incredibly dense, suggesting a huge iron core. It has a magnetic field, which is unusual for such a small planet. Its surface is covered in volcanic plains and strange hollows, depressions that might be caused by the evaporation of volatile materials. Bepi Colombo will help us understand why Mercury is so different from the other rocky planets and what its formation can tell us about the early solar system. Speaking of the early solar system, let's talk asteroids. Asteroids are time capsules. They are leftover building blocks from the solar system's formation 4.6 billion years ago. By studying them, we can understand what the primordial solar system was like. NASA's OSIRIS-REx mission successfully returned samples from the asteroid Bennu in September of 2023. Scientists are still analyzing those samples, and they've already found water-bearing minerals and organic molecules. China's Tianwen-2 mission is scheduled to launch in May of 2025. It will visit the near-Earth asteroid Kamo'olawa, a small asteroid that orbits the Sun but stays close to Earth. Kamo'olawa might be a fragment of the Moon ejected into space by a past impact. Tianwen-2 will collect samples from Kamo'olawa using touch-and-go and anchor-and-attach techniques, then return those samples to Earth. After that, the spacecraft will journey to the main asteroid belt to study a comet. NASA is planning the NEO Surveyor mission, scheduled to launch in 2028. NEO stands for Near Earth Object. This is an infrared space telescope designed to find and track asteroids that could pose an impact threat to Earth. The goal is to catalog 90% of asteroids larger than 140 meters, the size that could cause regional devastation if one hit Earth. There are also missions focused on asteroid deflection. NASA's DART mission, Double Asteroid Redirection Test, successfully impacted the asteroid Dimorphos in September of 2022, changing its orbit. This proved we can deflect an asteroid if we detect one on a collision course with Earth. ESA's Hera mission launched in October of 2024 to visit Dimorphos and study the aftermath of the DART impact. Hera will measure the size of the crater DART created, analyze the asteroid's composition, and gather data to refine our asteroid deflection techniques. And then there are missions to the outer reaches of the solar system. NASA's New Horizons spacecraft flew past Pluto in July of 2015, giving us our first close-up views of the dwarf planet. It then continued into the Kuiper Belt, a region of icy bodies beyond Neptune, and flew past the object Arrokoth in January of 2019. New Horizons is still operational, traveling through the Kuiper Belt, sending back data on the space environment at the edge of the solar system. NASA's Juno mission is orbiting Jupiter, studying the planet's atmosphere, magnetic field, and interior structure. Juno has made incredible discoveries, including detailed images of Jupiter's swirling storms and data on the planet's gravitational field that reveal what's happening deep inside the gas giant. The Voyager 1 and Voyager 2 spacecraft, launched way back in 1977, are now in interstellar space. They've left the solar system's protective bubble, the heliosphere, and are traveling through the space between stars, still sending back data about the interstellar medium. Voyager 1 is the most distant human-made object, currently over 24 billion kilometers from Earth. Signals from Voyager 1 take over 22 hours to reach us, traveling at the speed of light. These missions, all of them, are expanding the boundaries of human knowledge. They're exploring worlds we can only dream of visiting with crewed missions someday. But to support all this exploration, to communicate with spacecraft billions of kilometers away, to command rovers on Mars, to receive stunning images from the outer planets, we need infrastructure. We need the Deep Space Network. NASA's Deep Space Network consists of 3 massive radio antenna complexes located in California, Spain, and Australia. Together, they provide 24-hour coverage of the solar system as Earth rotates. These antennas can detect incredibly faint signals from spacecraft at the edge of the solar system and can transmit commands with enough power to reach distant probes. The DSN is a marvel of engineering, and it's constantly being upgraded to handle the increasing number of deep space missions. All of this, every mission, every discovery, every image of alien worlds relies on the infrastructure we're building, the rockets that launch these spacecraft, the communication networks that connect us to them, the laboratories where scientists analyze the data, and the people. Thousands of engineers, scientists, technicians, and dreamers working together to push the boundaries of exploration. But while we send robots to distant moons and planets, we're also learning to live and work in space closer to home. We're building orbital habitats. We're testing technologies for long-duration spaceflight. We're laying the groundwork for a future where humans don't just visit space, they live there. Let's talk about the orbital economy. Right now, approximately 400 kilometers above your head, people are living in space, not visiting. Living. The International Space Station has been continuously inhabited since November 2 of the year 2000. That's over 25 years of uninterrupted human presence in orbit. Astronauts and cosmonauts have rotated through in shifts, conducting experiments, maintaining systems, and proving that humans can survive and thrive in the harsh environment of space. The ISS is massive. It's about the size of a football field, with a pressurized volume of 915 cubic meters, roughly equivalent to a 6-bedroom house. It orbits Earth every 90 minutes, traveling at approximately 27,600 kilometers per hour. The station is a collaboration among 5 space agencies: NASA, Roscosmos, ESA, JAXA, and CSA, the Canadian Space Agency. Modules were launched over many years and assembled in orbit piece by piece, creating a sprawling structure with solar panels, radiators, docking ports, and research laboratories. What do astronauts do on the ISS? Research. Lots of research. They study how microgravity affects the human body. Bone density loss, muscle atrophy, vision changes, fluid shifts. This research is critical for planning long-duration missions to the Moon and Mars. They grow plants in space, testing agricultural systems that could provide food for future deep space missions. They study materials, science, combustion physics, and fluid dynamics in ways impossible on Earth, where gravity dominates everything. They test technologies, life support systems, 3D printers, robotic tools that will be needed for future exploration. The ISS has hosted crews from 20 countries. It's one of the greatest examples of international cooperation in human history, bringing together nations that have been geopolitical rivals on Earth. But the ISS is aging. It's been in orbit for over 25 years. Systems are wearing out. Modules are showing their age. NASA and its partners have extended the station's operational life to at least 2030, but its days are numbered. So what comes next? Commercial space stations. Several private companies are developing orbital habitats designed to replace or supplement the ISS. Axiom Space has a contract with NASA to build commercial modules that will initially attach to the ISS. These modules will include crew quarters, research laboratories, and a large windowed cupola for Earth observation. Eventually, Axiom plans to detach their modules from the ISS and operate them as an independent commercial space station called Axiom Station. The first Axiom module is scheduled to launch in the late 2020s. Once operational, Axiom Station will host government astronauts, private researchers, space tourists, and commercial activities. Blue Origin, in partnership with Sierra Space and Boeing, is developing Orbital Reef, a commercial space station designed to accommodate up to 10 people. Orbital Reef will feature modules for research, manufacturing, and habitation, plus a large window for Earth observation. Orbital Reef is designed to support a mixed-use business park model, government research, private companies conducting manufacturing in microgravity, space tourism, entertainment, and even media production. Imagine filming a movie in actual zero gravity. NASA has awarded contracts to both Axiom and Blue Origin to develop these stations, providing funding in exchange for guaranteed access for NASA astronauts and experiments. Northrop Grumman, the company that builds cargo spacecraft for the ISS, is also exploring commercial space station concepts. And then, there are smaller, more specialized platforms. Vast Space is developing Haven 1, a small commercial space station designed for short-duration missions. It's scheduled to launch aboard a SpaceX Falcon 9 in 2027. Think Orbital is working on modular space platforms that could be assembled in orbit for various purposes: research, manufacturing, satellite servicing. The vision is clear. Low Earth orbit is transitioning from a domain dominated by government-funded stations to a bustling commercial ecosystem. Multiple stations, each serving different customers and purposes, creating an orbital economy. But while the ISS and future commercial stations orbit Earth, there's another space station under construction in a very different orbit: China's Tiangong Space Station. Tiangong, which means Heavenly Palace, is China's independent orbital outpost. It became operational in November of 2022 after the launch and assembly of its three main modules: Tianhe, the core module; Wentian, the first laboratory module; and Mengtian, the second laboratory module. Tiangong is smaller than the ISS, with a pressurized volume of about 340 cubic meters, but it's designed for long-duration stays. 3 taikonauts typically inhabit the station at a time, conducting 6-month missions. As of late 2025, Tiangong has hosted multiple crews. The current crew, launched aboard Shenzhou 21 in October of 2025, is conducting scientific experiments, spacewalks, and technology demonstrations. Tiangong has faced some drama recently. In November of 2025, the Shenzhou 20 spacecraft, which was docked at the station, suffered damage from suspected space debris, cracking a window. The crew of Shenzhou 20 had to return to Earth aboard the newly arrived Shenzhou 21 spacecraft. China then launched Shenzhou 22 in an emergency uncrewed flight to provide the current crew with a safe ride home. This incident highlights the dangers of operating in low Earth orbit, where even tiny pieces of debris can cause catastrophic damage. China has big plans for Tiangong. They're developing the Xuntian Space Telescope, a large optical telescope that will orbit independently, but can dock with Tiangong for servicing and upgrades. Xuntian is comparable in capability to the Hubble Space Telescope and is scheduled to launch in late 2026. China is also testing new spacecraft. Mengzhou is their next-generation crewed vehicle designed to replace the Shenzhou spacecraft. Mengzhou is larger, with more room for crew and cargo, and it's designed for missions to the Moon as well as low Earth orbit. The first uncrewed test flight of Mengzhou is scheduled for late 2026, when it will dock with Tiangong to validate systems. Tiangong is open to international cooperation. China has invited other nations to send astronauts to the station. Pakistan has signed an agreement to send a Pakistani astronaut for a short-duration mission in the coming years. Other countries have expressed interest. Tiangong represents China's independence in human spaceflight. They were excluded from the ISS due to US restrictions on NASA cooperation with China, so they built their own station. And they've proven they can operate it successfully. Both the ISS and Tiangong serve as testbeds for technologies needed for deep space exploration. Long-duration life support, closed-loop water recycling, radiation shielding, exercise regimens to counteract bone and muscle loss, psychological support for isolated crews. Living in space is hard. Astronauts experience numerous health challenges. Bone density decreases at a rate of 1 to 2% per month in microgravity. Without countermeasures, astronauts returning from 6-month missions would have bones as brittle as an elderly person's. Muscles atrophy because they're not working against gravity. Astronauts exercise for 2 hours every day on specialized equipment to maintain muscle mass. Fluid shifts toward the head in microgravity, causing puffy faces, congestion, and sometimes vision problems. Some astronauts have experienced long-term changes to their eyesight after prolonged spaceflight. Radiation exposure is higher in space than on Earth's surface, increasing cancer risk. But we're learning how to manage these challenges. Astronauts on the ISS are healthier than ever, thanks to improved exercise equipment, better nutrition, and medical monitoring. And then there's the burgeoning space tourism industry. Blue Origin has been flying suborbital tourist flights aboard their New Shepard rocket since 2021. Passengers experience a few minutes of weightlessness and see the curvature of Earth before returning to the surface. As of late 2025, Blue Origin has flown dozens of paying customers, celebrities, and researchers on these flights. Virgin Galactic has also been flying suborbital space tourism missions using their Spaceship Two spaceplane. Passengers are carried aloft by a carrier aircraft released at high altitude and rocketed to the edge of space for a few minutes of weightlessness before gliding back to Earth. These are suborbital flights. They don't complete a full orbit, but they're still space. They're still an incredible experience that was impossible for civilians until very recently. Axiom Space has conducted private missions to the ISS. Axiom Mission 3 flew in January of 2024, carrying private astronauts to the ISS for a 2-week stay. These missions are incredibly expensive, tens of millions of dollars per seat, but they demonstrate that private individuals can visit orbital space. SpaceX has flown multiple private missions aboard their Crew Dragon spacecraft. The Inspiration 4 mission in September of 2021 was the first all-civilian orbital mission, with 4 private citizens spending 3 days in orbit. The Polaris Dawn mission in September of 2024 flew to an altitude of 1,400 kilometers, the highest humans have been since the Apollo era, and conducted the first commercial spacewalk. Space tourism is nascent, but it's real. And as launch costs decrease and commercial space stations come online, it will become more accessible. Eventually, not in the next few years, but in the coming decades, spending a week in orbit might be as common as taking a cruise. Expensive, sure, but achievable for many people. And the economic possibilities extend beyond tourism. Manufacturing in microgravity opens up entirely new possibilities. Certain materials, fiber optic cables, protein crystals for drug development, specialized alloys, can be manufactured with higher quality in microgravity than on Earth. Companies are beginning to explore this. Made in Space, now part of Redwire, has developed 3D printers that operate on the ISS. They've printed tools, parts, and even biological tissues in space. Varda Space Industries is developing spacecraft that can manufacture pharmaceuticals in microgravity and return them to Earth. Their first mission in 2023 successfully manufactured crystals of a HIV drug in space and brought them back for analysis. As access to orbit becomes cheaper and commercial space stations become operational, these activities will expand. We might see orbital factories producing materials impossible to create on Earth. All of this, space stations, space tourism, orbital manufacturing, is laying the groundwork for humanity's permanent presence in space. We're transitioning from an era where space is visited occasionally by highly trained astronauts to an era where people live and work in orbit routinely. And all of this is connected to the deeper exploration efforts. The technologies tested on the ISS inform Mars mission planning. The commercial space stations reduce costs, freeing up government budgets for Moon and Mars programs. The orbital economy creates jobs and industries that sustain public interest and political support for space exploration. It's all interconnected, and it's all happening right now. But let's zoom out even further. Because while we're building rockets, landing on the Moon, exploring Mars, and learning to live in orbit, we're also peering deeper into the cosmos than ever before, discovering things that challenge our understanding of the universe itself. Let's talk about the bigger picture. On Christmas Day 2021, an extraordinary event occurred. A telescope, the most powerful ever built, was folded up like origami, packed inside a rocket fairing, and launched into space aboard an Ariane 5 rocket from French Guiana, the James Webb Space Telescope. Its journey to its destination took 1 month. it traveled 1.5 million kilometers from Earth to a gravitationally stable point called the Sun-Earth L2 Lagrange point, where the gravitational forces of the Sun and Earth balance perfectly, allowing the telescope to orbit that point with minimal fuel usage. Once there, it unfolded. Its massive 18-segment gold-plated mirror deployed, its tennis court-sized sunshield unfurled, creating layers of protection to keep the telescope's instruments at near absolute zero temperatures. And then it opened its eyes. What James Webb has shown us in the years since is nothing short of revolutionary. It has captured images of galaxies that formed just a few hundred million years after the Big Bang. Galaxies that shouldn't exist according to our models. Galaxies that formed too quickly, too massively, forcing us to rethink galaxy formation. It has analyzed the atmospheres of exoplanets, planets orbiting distant stars, detecting water vapor, carbon dioxide, methane, and even sulfur dioxide in their atmospheres. These are biosignature gases, not definitive proof of life, but tantalizing hints. It has peered into stellar nurseries, showing us the birth of stars with unprecedented clarity. It has revealed the complex chemistry of the interstellar medium, the space between stars where the raw materials for planets and life accumulate. James Webb has looked at planets in our own solar system, Jupiter, Saturn, Neptune, revealing atmospheric dynamics and storm systems in exquisite detail. It has observed supernova, black holes, and quasars, providing data that helps us understand the most violent and energetic phenomena in the universe. The images Webb produces aren't just scientifically valuable. They're beautiful. They're awe-inspiring. They remind us that we live in a universe of unimaginable scale and complexity. But Webb isn't the only observatory expanding our cosmic horizons. The Hubble Space Telescope, launched way back in April of 1990, is still operational. It's been in orbit for 35 years, and it continues to make groundbreaking discoveries. Hubble operates primarily in visible and ultraviolet light, complementing Webb's infrared observations. In 2025, Hubble captured stunning images to celebrate its 35th anniversary, including views of Mars, planetary nebulae, star-forming regions, and nearby galaxies. Despite occasional hardware issues and the challenges of maintaining a 3-decade-old spacecraft, Hubble remains a workhorse of astronomy. Ground-based telescopes are also pushing boundaries. The Extremely Large Telescope, ELT, is under construction in Chile. When completed in the late 2020s, its primary mirror will be 39 meters in diameter, making it the largest optical telescope ever built. ELT will study exoplanet atmospheres, galaxy formation, and the nature of dark matter and dark energy. The Square Kilometre Array, SKA, is a massive radio telescope being built in South Africa and Australia. When operational, it will be the most sensitive radio telescope ever constructed, capable of detecting faint signals from the early universe and searching for technosignatures, signs of alien civilizations. And speaking of exoplanets, we're in a golden age of discovery. NASA's Transiting Exoplanet Survey Satellite, TSS, has been scanning the sky since 2018, searching for planets orbiting nearby stars. TESS has discovered thousands of exoplanet candidates, many of them in the habitable zones of their stars, where liquid water could exist. The European Space Agency's CEOPS mission is characterizing known exoplanets, measuring their sizes and densities to determine if they're rocky, gaseous, or something in between. NASA's SphereX mission, scheduled to launch in February of 2025, will conduct an all-sky survey in near-infrared light, studying the history of the universe, the formation of galaxies, and the distribution of water and organic molecules in star-forming regions. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will be a wide-field infrared observatory designed to study dark energy, exoplanets, and the structure of the universe. It's named after NASA's first chief of astronomy, Nancy Grace Roman, who played a pivotal role in the development of the Hubble Space Telescope. All these missions, ground-based and space-based, are converging on the same profound questions. Are we alone in the universe? How did galaxies, stars, and planets form? What is the ultimate fate of the cosmos? And here's the remarkable thing. We're getting answers. Not complete answers, not final answers, but real data-driven insights that are reshaping our understanding. We now know that planets are common, extremely common. Nearly every star in the galaxy has at least one planet. The Milky Way contains hundreds of billions of planets. We know that many of these planets are in the habitable zones of their stars. We found rocky planets similar in size to Earth, orbiting in regions where temperatures could allow liquid water. We've detected organic molecules, the building blocks of life, in interstellar space, in comets, in asteroids, and in the atmospheres of exoplanets. We haven't found definitive evidence of life beyond Earth yet, but the conditions for life, liquid water, organic chemistry, energy sources, appear to be widespread in the universe, and the search is intensifying. The next generation of telescopes will be capable of analyzing exoplanet atmospheres in enough detail to search for biosignatures, combinations of gases that, on Earth, are produced by living organisms. Oxygen and methane together, for example, is hard to explain without life because these gases react with each other and disappear unless they're continuously replenished. If we detect biosignatures on a nearby exoplanet, it would be one of the most significant discoveries in human history. It wouldn't tell us what the life looks like, but it would tell us we're not alone. And all of this cosmic exploration feeds back into our exploration of the solar system. Understanding how planets form helps us interpret what we see on Mars, Venus, and the icy moons. Studying extreme environments in the universe, radiation-blasted planets, ice-covered moons, worlds with exotic chemistries, helps us understand where to look for life closer to home. The technology developed for space telescopes often finds applications in planetary missions. The sensors, the communication systems, the data processing algorithms, they're all interconnected. And then there's the impact on Earth. Space exploration drives technological innovation that improves life on our planet. Satellite technology, developed for space missions, enables GPS navigation, weather forecasting, climate monitoring, disaster response, and global communications. Medical technologies developed for monitoring astronaut health have been adapted for use in hospitals and clinics. Materials science research conducted in microgravity has led to stronger alloys, better insulation, and advanced manufacturing techniques. Water purification systems developed for the ISS are now used in remote communities without access to clean water. The economic impact is substantial too. The global space industry is worth hundreds of billions of dollars and employs millions of people. Launch providers, satellite manufacturers, ground stations, data analytics companies, it's a vast ecosystem, and it's growing. As launch costs decrease and access to space becomes easier, new industries are emerging. Satellite internet constellations like Starlink are bringing high-speed internet to remote areas. Earth observation satellites are helping farmers optimize crop yields. Space-based solar power is being explored as a potential clean energy source, but perhaps the most profound impact of space exploration is cultural and philosophical. When you see images of Earth from space, a fragile blue marble suspended in the infinite blackness, it changes your perspective. National borders disappear. Political conflicts seem petty. You realize we're all on this small planet together, sharing the same atmosphere, the same oceans, the same fate. This perspective, sometimes called the overview effect, has been described by countless astronauts. It's a sense of unity, of interconnectedness, of responsibility for our planet and each other. Space exploration also inspires. It shows us what's possible when humans work together toward a common goal. It demonstrates that we can solve incredibly difficult problems if we're willing to invest the time, resources, and ingenuity. Kids who watch rocket launches, who see images from Mars rovers, who learn about missions to distant moons, they're inspired to pursue careers in science, engineering, mathematics. They become the next generation of explorers, inventors, and leaders. And let's not forget international cooperation. Despite geopolitical tensions on Earth, space has been a domain where nations collaborate. The ISS is a testament to this. American astronauts and Russian cosmonauts living and working together, despite the conflicts between their governments. The Artemis Accords, signed by over 30 nations, establish principles for peaceful exploration of the moon and beyond. While not every nation has signed, it represents a growing consensus that space should be explored for the benefit of all humanity. China has invited international partners to collaborate on their space station and lunar programs. ESA works with NASA, JAXA, Roscosmos, and others on joint missions. Space is one of the few areas where international cooperation is not just encouraged, it's essential. No single nation can explore the solar system alone. The challenges are too great, the costs too high, the expertise too specialized. And so we come together. We build spacecraft together. We share data. We collaborate on science. We dream together. This is the convergence. Technology, science, economics, culture, philosophy, all coming together, all driving us forward, all pointing toward the same future. A future where humanity is not confined to a single planet. A future where we walk on multiple worlds, where we mine asteroids, where we build cities on the moon and Mars. A future where we answer the ancient question of whether we're alone in the universe. That future isn't some distant fantasy. It's unfolding right now. The missions are launching. The hardware is being built. The timelines are already locked in. And as we reach the end of 2025, the new space race is no longer a build-up phase. It is already in motion. This year alone, NASA's SphereX observatory launched and began its all-sky survey, mapping the structure and history of the universe in unprecedented detail. China launched its Tianwen-2 mission, beginning a complex journey to collect samples from a near-Earth asteroid before continuing onward toward a comet. On the moon, commercial landers began delivering new scientific payloads, including missions designed to explore permanently shadowed regions where water ice may be hiding. Japan continued refining precision landing technologies on the lunar surface. India pushed its Chandrayaan-4 sample return program closer to readiness. At the same time, SpaceX accelerated Starship testing, demonstrating increasingly complex recovery and orbital refueling attempts. Rocket Lab maintained a steady cadence of Electron launches while advancing development of its larger Neutron rocket. Blue Origin began additional New Glenn test flights, refining booster recovery systems. And across Earth's orbit, dozens of new satellites were added to communication networks, climate monitoring systems, and scientific observatories. By the end of 2025, spaceflight is no longer ramping up. It is already accelerating. Now everything shifts into a new phase. In 2026, humans finally leave Earth orbit again. NASA's Artemis 2 mission is scheduled to carry 4 astronauts on a crewed flight around the moon, the first humans to do so in more than half a century. Blue Origin's Blue Moon lander is expected to attempt its first uncrewed demonstration at the lunar South Pole. China's Zhontian Space Telescope is set to begin operations alongside the Tiangong space station. The Bepi-Colombo spacecraft is scheduled to enter orbit around Mercury and begin its long-awaited science mission. Rocket Lab prepares its Venus Life Finder mission, designed to search for chemical signatures in the planet's upper atmosphere. And Europa Clipper performs a critical gravity assist flyby of Earth on its long journey toward Jupiter. By 2027, the new lunar era reaches a historic milestone. NASA's Artemis 3 mission aims to land astronauts at the moon's south pole. returning humans to the lunar surface for the first time since 1972. Surface operations follow. Sample collection, instrument deployment, long-duration exploration. Construction of the Lunar Gateway continues in orbit around the Moon. Rocket Lab's Neutron rocket enters operational service, and the first private commercial space station modules prepare for launch. In 2028, deep space science surges again. Dragonfly launches toward Saturn's moon Titan. NEO Surveyor begins a dedicated hunt for potentially hazardous asteroids. Japan launches a mission to study one of the most unusual objects in the inner solar system. Europe sends a spacecraft that will simply wait in deep space for a pristine comet no one has discovered yet. By 2030, the outer solar system comes back into focus. Europa Clipper arrives at Jupiter. The Lunar Gateway expands. China's crewed lunar program approaches full readiness. Mars sample return components may finally begin launching, and in the decade that follows, the pace does not slow. Dragonfly flies across Titan. Permanent lunar bases begin taking shape. Mars samples arrive back on Earth. Commercial space stations host researchers and tourists. Thousands of satellites reshape global infrastructure. And for the first time in history, human missions to Mars begin to look not just possible, but inevitable. Do you see the pattern? This isn't slowing down, it's accelerating. We're on an exponential curve. Each mission builds on the previous one. Each success makes the next goal more achievable. Each technology demonstration unlocks new possibilities. In the 1960s, we went from Alan Shepard's 15-minute suborbital flight to Neil Armstrong walking on the moon in just 8 years. 8 years. We have that same energy now, but distributed across many more players. It's not just NASA anymore. It's NASA plus SpaceX, plus Blue Origin, plus Rocket Lab, plus ESA, plus JAXA, plus China, plus India, plus dozens of other companies and countries, all pushing forward simultaneously. And the motivations are diverse. Some want scientific discovery, some want economic opportunity, some want national prestige, some want to ensure humanity's long-term survival. Some simply want to explore because that's what humans do. All these motivations, all this energy, all this capability, it's converging into a moment of explosive growth in space exploration. Why now? Why is this happening right now in the 2020s? Because multiple factors have aligned. Launch costs have dropped dramatically thanks to reusability. It costs a fraction of what it did 20 years ago to put a kilogram in orbit. Computing power has exploded. The smartphones in our pockets have more processing power than the computers that guided Apollo to the moon. This enables autonomous spacecraft, sophisticated sensors, and real-time data analysis. Manufacturing technology has advanced. 3D printing, precision robotics, advanced materials, all make spacecraft cheaper and faster to build. International collaboration has expanded, spreading costs and expertise across multiple partners. Private investment has flooded into space. Billionaires like Elon Musk and Jeff Bezos are investing tens of billions of their own money. Venture capital is flowing into space startups. The economic case for space is becoming clearer. Public interest is high. People are excited about space again. They watch rocket launches online. They follow rover missions. They share images from James Webb. This cultural enthusiasm translates into political support and funding. All these factors together create a self-reinforcing cycle. Success breeds more investment. More investment enables more missions. More missions generate more data and excitement. More excitement attracts talent and funding. And the cycle continues. But let's not forget the human element. Behind every mission are thousands of people. Engineers designing spacecraft, technicians assembling rockets, scientists planning experiments, mission controllers monitoring data, administrators securing funding, communicators sharing discoveries with the public. These are real people with families, dreams, and passions. They work long hours, solve impossible problems, and push the boundaries of what's achievable. And then there are the astronauts, the individuals who ride these rockets, who float in space stations, who will walk on the Moon and Mars. They're test pilots, scientists, engineers, doctors. They train for years, mastering every system, preparing for every contingency. They know the risks. They accept them anyway because the call to explore is stronger than the fear. The Artemis II crew, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, are preparing right now. They're training in simulators, studying flight plans, conducting underwater spacewalk practice, building the skills they'll need for their journey around the Moon. Somewhere on Earth right now, a child is watching rocket launches, dreaming of distant worlds. That child may one day walk on Mars. This is the moment we're living in. This is the era we get to witness. And it's only just beginning. Everything we've explored, the Moon, Mars, deep space, new rockets, new stations, new worlds, is part of a single story. Humanity's transformation from a planet-bound species to a spacefaring civilization. The new space race isn't about who gets there first. It's about what lasts, what gets built, and how far the generations after us will be able to go. And whether we realize it or not, we're all part of it. The new space race is already underway. If this journey fascinates you, subscribe to Whispering Wonders of Science. We'll be here to witness every step of it together. Because the future of space is not approaching, it's happening. Right now. Clear skies.